Question is, every day, millions of people, including yourself and myself, we trust food that we cannot see being made by people that we will never meet in countries that we may never visit. So, how does the world make this impossible trust possible? Right? That's where the module 10 come in. Codex HACCP as a universal language for food safety. And that's our topic today. We will demonstrate that not only through theories and scientific basis only, but we will also demonstrate through practices, step by step practices. All right. And we will explore how the world align on prevention because the global trust requires a shared preventive language, right? And we are going to go through HACCP training. This is a module 3 equivalent training that is going into depth and exploration, and we will walk through companies with vivid colors to explain and to demonstrate the implementation. Before we dive in, let me quickly highlight our targeted audience that this course is designed for. We designed this course to serve the broader community in primary industry and food manufacturing sector. We designed it for primary and production manufacturing sector, including farmers and primary producers. We also designed this course for food and ingredient manufacturers and also for multinational food companies. And we have designed our course for small scale processors also. And this course is also tailored to distribution and service sector. It's for cold storage and logistics providers. It's for importers and exporters. It's designed for retailers and supermarkets. It's also designed for food service and catering chains. And this course is designed for professional specialists. It's tailored for food safety managers and for quality assurance teams. And it's for internal and third party auditors. It's also designed for food consultant and technical specialists. This course also is designed for governance and oversight. It's designed for regulatory professionals, for NGO and public health officials, and also is designed for supply chain risk managers and for senior leadership teams. Right? In our design process of this course, we made it in a way that it must make sense to everyone in the mentioned categories, from small farmers to global corporations, because we are going to speak the universal language of food safety as usual. And in case you want to go through the previous modules from 1 to 9, they are on our YouTube channels. Now, let's explore how we will demonstrate. We will go from theory to practice. And this course is going to be your HACCP implementation roadmap because you will have all the tools you need to implement the HACCP from scratch in your organization. And having explored why HACCP become essential for global food safety with our previous modules, I hope you watch them. If not, you can explore that. Now we are transitioning to the practical applications of this critical system. This section, Module 10 here, will provide a step-by-step guidance with real-world examples. We will demonstrate through real companies, and we will use the universal tools that we will give you also that you can utilize tomorrow in your own organization. Once you complete this module, you'll master the principles and steps. You will You will gain proficiency in the 7 principles and 12 steps with practicals and real world examples. And also you will learn you will learn world class practices, the best practices in the world from the companies. You will discover the implementation strategies from leading global food safety organizations. And also, you will access universal tools. You will utilize those practical tools that we are going to give you and the templates for immediate applications in your operations. Now, let's take a look at HACCP framework overview to understand the complete HACCP structure. So, before the implementation, we need to understand how the pieces fit together. We need to understand the 7 principles, which are the scientific logic of HACCP, the 7 principles of HACCP, and also we need to understand the 12 steps of HACCP, which are the implementation sequence of HACCP implementation. And also we need to understand the documentation systems, which are the evidence and communication layers of HACCP. All right. So we're going to have an overview of the 7 principles and on 12 steps and on documentation requirements. Then we will dive deeper. The key insights here, you have to know that the 7 principles are embedded within the 12 steps of HACCP. All right. So the 12 steps are the how to do the HACCP, how to implement the HACCP, and the 7 principles are the what you need to do as implementation of HACCP. If you look at the visual representation here, you will see the inner circle is the HACCP core principles, the 7 principles that define the food safety logic, and the second layer are the foundational steps from step 1 to step 5, which are the preparation and the analysis of the HACCP. Sorry. And then in the outer layer, you have the mapped implementation, the step 6 to step 12, which are correspondent to principle 1 to 7. So essentially, the 12 step, you have a step 1 to step 5 are the preparation of HACCP, and then from step 6 to step 12 are the principles of HACCP. And we will demonstrate that. Okay? Now, let's have an overview first on the 7 principles, which are the scientific logic behind the HACCP. So the first principle of HACCP is to conduct the hazard analysis. And this principle requires us to identify potential biological, chemical, or physical hazards that could make food unsafe. This is the requirement of the first principle. Then if we go to the second principles is to determine the critical control points, CCPs. So in second principle, it requires us to pinpoint the steps in the process where control can be applied to prevent, eliminate, or reduce a food safety hazards to an acceptable level. So this is the second principle to determine the critical control point. The third principle of HACCP is to establish critical limits. All right. And the third principle requires us to set maximum and minimum values for biological, chemical, or physical parameters at each CCP to ensure hazards are controlled. The fourth principle of HACCP is to establish monitoring procedures. In the fourth principle of HACCP, we are required to define methods and frequencies for observation of measurements to assess whether a CCP is under control or not. So the principle number 4 is to establish monitoring procedures. The principle number 5 of HACCP is to establish corrective actions. And this principle requires us to plan actions to be taken when monitoring indicates a deviation from critical limits at a CCP. This means we need to plan in advance. In case of deviation, what do we need to do? This will allow systematic and fast response for corrective actions. The sixth principle, or principle number 6 of HACCP, is to establish verification procedures. This principle requires us to implement activities to confirm that the HACCP system is working effectively and achieving its intended food safety goals. All right. And the final principle of HACCP, principle number 7, is to establish record keeping and documentation. This principle requires us to maintain accurate and comprehensive records of all HACCP plans, elements, and operational activities. This is the overview of the 7 principles of HACCP. And these principles represents the scientific foundation of HACCP. Next, we will have an overview of the 12 steps that operationalize these 7 principles. The 12 steps of HACCP, let's have an overview, are the implementation sequence of HACCP. The first step of HACCP is to assemble the HACCP team. That means to have number of people that compose to become HACCP team, and they must be from different backgrounds and disciplinaries. And when you assemble the HACCP team as the first step, then step number 2, you need to describe the product. As a team, you need to describe the product. Once you describe the product, which is the second step, then you move to step number 3 to identify the intended use of the product. So this is a step 3 to identify the intended use of the product. Then step 4 is to construct the flow diagram from ground up. So step 4 requires us construct the flow diagram including all the steps from receiving to distribution, all right, of the product. When we receive the raw material, what do we do with it? All the processes, all the steps involved until the distribution of the final product. Once we construct the flow diagram, which is usually done using the references and done in offices, then step 5 is to take that flow diagram to the shop floor and verify it. So we need to verify the flow diagram on site. This is the step 5 and must not be skipped. So once you have constructed your flow diagram, you need to take it on the ground during the operational hours and verify it. Then step number 6 of HACCP is to conduct the hazard analysis. Okay, after you have verified your flow diagram with all the steps that are aligned with actual work, then you come back and you conduct the hazard analysis. And this is step 6 is correspondent to principle number 1. So now you have seen that 5 steps are the preparation steps. And from step 6, that's when you start applying the principles. So step 6 is to conduct hazard analysis, principle 1. Once you have conducted your hazard analysis, then you move to step number 7 to determine the critical control points. And this is correspondent to principle number 2. Once you have done that, then you move to step number 8 to establish critical limits. And this is correspondent to to principle number 3. And once you are done with that, you move to step number 9, which require us to establish monitoring procedures. And this is also correspondent to principle number 4. And in step 10, You need to establish corrective actions, and this is correspondent to principle number 5, establishing corrective actions. And step 11 is to establish verification procedures, which is correspondent to principle number 6. And then step number 12 is to establish documentation and record keeping, which is correspondent to principle number 7. So essentially, to memorize it correctly from step 6, just consider the step 6 is principle 1 and then count until 12 correspondent with each principles, and that's how you operationalize the principles of HACCP. This is the overview. So step 1 again is the preparation, is to prepare the foundation, and from step 6 to 12 is to apply the principles systematically. Now, since we finished with the overview, let's dive deeper, a little deeper into the steps one by one. All right. Now, in step 1, let's start with step 1 is to assemble the HACCP team. All right. Just give me a second. Let me drink some water. Step 1 is to assemble the HACCP team. All right. Now, what this step requires? This step requires us to form a multidisciplinary team with knowledge of the product and of the process and of the hazard. So that's why it must be multidisciplinary. You have people who know more about product and people who know more about process and people who know more about hazard. So we compose a team here. And why is it matter to have multidisciplinary team? Because hazard cannot be done by one person. An effective hazard analysis requires diverse expertise, and every input from each person matter. Now, let me demonstrate with the real world example of the team composition. Here you can see on your left side column is where the roles of the team. In the middle, you have why we need this team member justification. And in the right column, you have the example from seafood processor. So we are composing this team in seafood processor facility. And you can replicate this table to compose your HACCP team. The first role, we have production manager as a member of the HACCP team, and justification of why we need them is because they know the actual process reality. So we invited Luke, who is the production manager with 15 years on processing floor. Then also we needed quality manager. The reason is that quality manager understands the testing and verification. So we include James, who is a microbiologist and a quality manager. Then we include the maintenance lead. The reason we included maintenance leads because they know the equipment capabilities and limits. So we include Chand, who has engineering background. Then we included sanitation supervisor. The reason is that because they understand the cleaning and contamination risks. So we included Deng, who is sanitation certified. Then we included external expert, but sometimes you can escape this. In this case, we include external expert, and we need the reason we need the external expert because they provide specialized hazard knowledge. In this case, we included Wall, myself as food safety consultant. So here you have the real example of HACCP team that is composed of 5 members. Now, to follow the best practices in the world, you could do the following. To compose your HACCP team, you need to include the line workers who operate CCPs daily. All right. This is what the best companies in the world do. And also, you need to rotate the team members annually to prevent the blind spot. Not only that, but also you are spreading the knowledge organizational wide. So once you include different members every year and you train them, that means eventually most of the members of the organization will be trained on HACCP, will have deep knowledge, and will take proactive actions for food safety initiatives. And also, the other best practice you can do is provide HACCP training to all team members before starting. They might have different background and different expertise, but to have aligned in HACCP principles and HACCP step training is essential for seamless and effective implementation. So the best companies in the world conduct HACCP training before starting. The common mistakes to avoid when composing your team here is when creating a team of managers who don't know the actual process details. Some companies do it and they think it's a prestige, but actually you miss out on the critical elements that the line workers or the mechanic can bring to the table. And you need to have team from diverse background. Therefore, avoid this mistake of creating a team of managers who don't know the actual process details. Regardless of their knowledge, you need to have from different background and different levels. The tools you can use tomorrow here for team composition, you can create charter templates of HACCP team, and you should include the definition of the roles, responsibility, and meeting schedules. So now this is the first step is to compose the team, and now you have the blueprint to do it correctly. Now let's move to the second step. In second step here, we need to describe the product. Second step of HACCP, we need to describe the product. So why this step requires description of the product is essential because the complete description of the product, including composition, structure, processing, packaging, and storage and distribution. And why it matter? It matter because the product characteristics determine which hazards are relevant and how they must be controlled. Let's demonstrate with the real-world example of the product description, the second step of HACCP. And here we have ready-to-eat sliced deli turkey. If you look at the table here, you have on your left side here, all right, in the left side, you have product characteristic. The middle column, you have details. And in the right column, you have the hazard relevance. And you can use this table for your product description. So we start first with the product name. It's a sliced oven roasted turkey breast. The composition of the product is turkey breast, water, salt, sodium phosphate of 2%. And the hazard relevant for the composition here, this product supports listeria growth because it contains high moisture and low acid. So we need to also note down the relevant hazard, the relevant hazards to the product characteristic. Then you look at the physical property of the product. It contains pH at 6.2 and water activities range at 0.97. The hazard relevance here for physical properties is a high risk for pathogen growth. All right. Sorry, let me go back here. Yep. The fourth characteristic is the processing of the product. And here it must be cooked to 71 degrees Celsius of the internal breast of the product, not the external, but the internal part of the product must reach 71 degrees Celsius, and then slice the product after the cooking, post cooking. And the hazard relevant here, we have post lethality contamination risk, because after you cook, you conduct the slicing, and here the cross contamination could happen. So the hazard relevant is post lethality contamination risk. Then we have the packaging of the product, and the details here we package in vacuum sealed bags and with the modified atmosphere of CO2 and N2. The hazard relevance to the packaging here is that the extended shelf life, but the vacuum sealed bag extends shelf life but doesn't kill pathogen. Then we move to the next characteristic of the product, which is the storage and distribution. The details here, we store it and distribute it through a refrigerated warehouse and also through a refrigerated truck, and we maintain 0 to 4 degrees Celsius throughout the storage and transportation. Relevant hazard here, you have temperature abuse. It means that the rapid growth will happen. Then we have shelf life. Shelf life as a characteristic of the product. And the shelf life here is 4 to 5 days if refrigerated and unopened. The hazard relevant to the shelf life here, the long shelf life allows more time for growth of the pathogens if the product is contaminated. The final characteristic of the product is intended consumer, and the product is for general public and it's ready to eat. Relevant hazard here, relevant potential hazard, we don't have kill step by the consumer, so the product need to be controlled. This is how you conduct the table for the second step, which is description of the product. So you make a table like this, you note down the product characteristics and the details and the potential hazard relevance to the characteristic. All right. This is how you do the second step in the best practice. And for the whole best practice also, you must include photos. All right. Just to be the top of the top, you should include photos, the specifications of the product, and lab analysis results in the product description. All right. Do that. And mainly for those who implement HACCP, you have potential of exports. So exploring international markets require us to always strive for the best practices in the world. So you should include photos, specifications, and lab analysis results in the product description. All right. So the tools you can use tomorrow for steps 2, the product description of the HACCP, is to create a template for product description with all the required fields. All right. That's step number 2, the product description. Okay. Now let's move to step number 3. Step 3 is to identify the intended use and consumer. This is step number 3 of HACCP implementation. Identify intended use and consumer. So what this step requires here? This step requires description to describe the expected use of the products and identify the target consumers, including vulnerable populations. All right. Why does this step matter? It matters because the same hazard has different risk level depending on who consumes the product and how they use it. All right. Baby have different tolerance from an athlete or a healthy adult, and also the immunocompromised individuals, the elderly, and also the pregnant women. So people have different tolerance limits. All right. Now let's look at the real world example for comparison here for identifying the intended use. First, we have product A, raw chicken breast. The intended use here is to be cooked by consumers to 74 degrees Celsius. And the target consumer here are the general public, and the vulnerable groups must maintain the standard precaution. And for the hazard tolerance, we have salmonella is acceptable here because the product will be cooked, and the labeling required here is to label our product to keep refrigerated and cooked thoroughly. Now, the same product, but in here in uh, product B is a pre-cooked chicken breast, same raw material, but here is ready to eat. We are not selling raw, so the intended use here is ready to eat and no further cooking. The target consumers, we have general public, including children, and vulnerable groups are pregnant women, elderly, and immunocompromised. The hazard tolerance here is we must set at zero tolerance for Listeria monocytogenes, and the labeling requires here is to keep refrigerated. This is ready to eat. All right. So the critical insight here that we can take away, we have the same raw material, which is chicken, but completely different HACCP requirements based on intended use. All right. To implement the best practices in the world, you could do the following. You could conduct consumer research to understand actual use and not just the intended use. And also, you could identify the misuse scenarios. For example, consumers will not reheating the RTE or ready to eat products. So you identify the misuse scenarios and you place the controls. And also you consider the special protocols for product targeting vulnerable populations. All right. When you are in this step of the intended use, for the best practices, you include those three here in identifying the intended use, which is step 3 in HACCP implementation. But the tool you can take with you tomorrow now for step 3, just to take a note, you can create a worksheet for intended use with consumer profile checklist. All right. And as we progress further, you will know which information also or where to start and what to do. All right. Let's go to step number 4. Step number 4 of HACCP implementation is to construct the process flow diagram. That's step 4 in HACCP implementation. What this step requires, it requires us to complete diagram showing every step in the process from receiving raw materials to distribution of finished product. Why this step matters here? It matters because you cannot identify hazard at the steps you haven't documented. So the flow diagram is the foundation for hazard analysis. With the real world example for step 4, constructing flow diagram, you have here this simple flow diagram of the pasteurized orange juice, real world example. So first step is receiving fresh orange from growers. All right, here. And then you move to the next step, which is storage to store your orange in cold storage at at between 4 to 7 degrees Celsius for 24 hours to 48 hours. So once you store it here, now you can, once you want to move it to the production line, first you move it to the washing. And washing here, you may use automated brush washer with sanitizer. All right. Once you're done washing here, then you move to inspecting the material to remove the damaged fruits. And you can do this manually, okay, to remove the damaged fruits. After that, you move it to extractions through machinery to make the juice. So this is a simple flow diagram how you need to construct the physical representation, all right? So you construct like this. So what you need to include in your actual flow diagram, you need to include all the process steps, no matter how small the steps would need to be included. And also all the inputs must be included, including ingredients, packaging, water, and air. And also you should include all the rework loops and include all the storage points and include temperature time at each step as applicable. All right? Those are what you should include in your actual flow diagram construction. For the world-class practices or the best practices in the world, you should use standard flow chart symbols, and also you include actual equipment names and locations, and you show parallel processes clearly, and you color code different product lines. All right. So for this step 4, constructing the flow diagram, I hope this is clear. This should guide you to construct your own flow diagram or to refresh your memory at least. Now, the tool you can use tomorrow, you could create a flow diagram template with the standard symbols and checklist of elements to include. And you can prepare such documents until when you have your updates or when you are implementing. Just use the time you have to create such documents. They are helpful if you don't have one already, or you can update the one you have, all right, to include such elements and the best practices in the world. That is step 4 of HACCP implementation. Now let's move to step 5 of HACCP implementation. Step 5 requires us to verify the flow diagrams on the side. Remember in the beginning, during the overview, when we said we need to go to the shop floor and verify? This is a step that you should never skip. If you skip it, you will mess up everything. And also during the audit, you could have major non-conformance here. All right. So you need to verify flow diagram on the side. All right. Now, during the verification of flow diagram, first, why do we need this step? This step is required because the hazard team must walk through the entire process during the operating hours. Okay, like we said earlier, you don't go there during the off time or uh, during the holiday. You go there during operating hours. Okay, you go during operating hour so that you can see the actual work being done, which is different from work being imagined, and you will find a lot of things. And I will demonstrate as we go through. All right. So Why does this step matter? It matters because the flow diagram that we created in Office are usually wrong. So the reality is on the production floor, which will reveal the critical details, especially when people are working, okay? Now, let me demonstrate that with real-world examples on what on-site verifications reveal. So we conducted this in one of the facilities. We did the verification on the floor. And in our flow diagram, we noted that the cooked products moves directly to packaging. But when we went to verify, we discovered that the cooked product sits on cooling table for around 15 to 45 minutes in room temperature. This is what we found in reality there when we went to verify our flow diagram. And the impact here, we have uncontrolled time temperature, the 15 to 45 minutes. This is a window for potential hazard growth here or contamination. So we didn't know that when we drafted in the office, but when we went on the floor, we discovered this is the case. Second thing we discovered when we went to verify on this floor, in our diagram, we noted that there are separate raw and cook area. But when we went to verify, we found the same employee was moving between areas without changing gloves. All right? This is a real case scenario. We found the operator freely moving around, just, between uh, ready to eat areas and going to raw areas and not changing gloves. Very dangerous. Cross contamination pathway here is not documented. So we documented that and we applied control measures that we will demonstrate later on. And also, the third discovery we found, initially we noted in our flow diagram that the rework is added at the mixing stage. When we went there during when they were working and they were adding the rework, we found out that the rework sometimes is added after the pasteurization. All right? And that is dangerous. So unpasteurized materials are entering the pasteurized product. If we didn't go on the shop floor, we would have never known. But this is the reality we went during the operating hours. So you need to do that. When you are going to verify, go during the operating hours and you will find a lot of critical things that you are missing out. All right? Also, you need to create a checklist that you can take with you for verification. Because if you just go there blindly with your diagram, you will forget where to start and where to finish. So you need to have a checklist, okay? And this is a checklist here that you can create similar. Just take notes. First, in your checklist, you need to note down to tick the box of the work process during the actual production. So you will never know, you will never forget and go there during the off time. So your checklist must force you. I forget the word here. Must force you to uh, must oblige you to go during the production hours, and as a requirement, put that note down in your verification checklist on site. Okay, and then also put a line down in your verification checklist that you need to interview the operators at each step, not the manager, not the the maintenance guy. You need to you need the operator. Operator will give you a real picture in life, real picture in the process. Okay, so put a note down also that you will you'll interview the operator at each step. Then you need to observe the actual practices. Put this note down too. I don't want you to go there and sit in the office because it's too hot in the process floor. No, you need to put this down, okay? Not just procedures, you need to observe the actual practices. Sometimes you interview and they will tell you something, and then you need also to just observe by yourself, all right? And this doesn't happen over a day. You can take many times to visit frequently as much as you need to feel that this is enough, enough, right? Observation. Take that note in your checklist. And also, you need to measure the actual time and temperature. All right. For example, if your flow diagrams or the description of the product is telling you that you need to cook it for 74 degrees Celsius for 15 minutes, okay, that's what the validation tell you. That's what the science tell you. But also you need there and to verify that that's actually happening. Okay, for CCP steps, for example. So note this down. You need to measure the actual time and temperature by yourself. All right. And also, you need to photograph, to take photos. This is very important here. I don't want you to go there and come back and you forget where you were. Photos will link your memories, all right? And also will retain for the legacy and just in case of reference, easily you know where to go or the next person know where to go. All right? Let me see what's going on here. So you need to take the photos. Okay, I knew it. Something was going on. Anyways, let me just. Okay. All right. Um, we said you need to take the photos. All right. Just give me a second. Let me see something here. Give me a second, guys. All right. Everything is fine. Seems like we are recording. Yeah. Uh, all right. Here. All right. Just give me a second. Yep. You need to take the photos at each step, and then you need to document all the inputs and outputs. All right. And then you need to identify all the reworks and recycling loops also. So take this for your verification checklist. Take all these points and use them when you are going to verify on the shop floor. And also, there are additional points here in case, for the best practices on the wall, you can follow this. You need to verify during different shifts, okay? Come at night shift, during the second shift, morning shift. This is what the best practices and their leaders in the world, that's what they do. They come in during different shifts to verify because the practices are different. And also, best practices, you need to verify during different products because of the changeover risk, uh, reveal the risk, okay? For instance, if you are changing between allergen and non-allergen, just an example, the changeover right there requires a robust cleaning and ATP testing and environmental monitoring, all right? So when the change, it reveals new risks and it reveals also new procedures. Or sometimes when you are changing the size also, the size of the output. Okay, if you are doing packaging, you are packing in 50 kg, for example, the flour for bakery, and then you change to 10 kg. It also reveals different risk, all right, and different speed. So you need to do that for the best practices in the world. And also, you need to repeat the verification annually or when the process change. All right? This is one of the best practices, and you need to follow that in order to be one among the best. And I know you can do that. All right? Now, the tools I want you to take home and use it tomorrow, you need to create a checklist for on site verifications and photo documentation templates also. Create that and let me know in the comment section if you need help. I will send it to you. All right. Just a second. Now you see this is a step 5, okay? To verify the flow on the side. This is how you do it. I hope that's clear and you can replicate that, or I hope it also refresh your memory if you have done it already. Right? Now let's move to step number 6, okay, which is correspondent to principle number 1. Step 6 is to conduct the hazard analysis to identify the hazard first. Before we evaluate, now we will first identify, okay? Step 6. All right? Now, what this step requires? The identification of the hazards. We need to identify and evaluate all the potential biological, chemical, and physical hazards at each step in the process. All right? This is the requirement of this step. Why it matter? This step matter because this is the foundation of HACCP. If you miss hazard here, my friend, you cannot control it later, okay? So simply, this is the foundation. Hazard analysis critical control point, HACCP, HACCP, okay? So this is where you identify the hazard and you evaluate, you identify the hazard analysis. You here, you analyze them, you identify them and you evaluate them, all right? So this is step number 6. And there are 3 categories here, as we said. First, you have biological hazard, the microorganisms, all right? So you need to identify them. And commonly here we have the bacteria. We have Salmonella, Listeria, E. coli, O157H7, and Campylobacter, and Clostridium botulinum. Those are the bacteria. And then we have the viruses, including norovirus and hepatitis A. And we have parasites, also biological hazards. We have Trenchinella and anisakis, all right? Those are the parasites. So those 3 are the biological hazards, and they are the most common and the most dangerous category. So you need to identify your hazard thoroughly. And then the second category are the chemical hazards. And chemical hazard, we have naturally occurring chemical hazard such as mycotoxin and camprotoxin or histamine and ciguatoxin and allergens. Those are the naturally occurring chemical hazards. And then we have the intentionally added hazards, chemical hazards, including pesticides and veterinary drugs and food additives if we add them in excess quantities. Those are also chemical hazards. Then we have unintentional added chemical hazards, including cleaning chemicals, lubricants, and sanitizers. Those are chemical hazards also. Second category. The third category are the physical hazards. And in physical hazard, we have hard or sharp objects such as glasses, metals, stones, wood, plastic, and bones. And then we do have also the choking hazards such as large pieces of the product also, right? The large pieces of the product itself are physical hazard because they are dangerous for children and elderly. Okay? Those are the 3 categories of our hazard. And then to demonstrate that with the real world example, our hazard analysis for the cooked rice. So now first we are identifying the hazard, okay? And then we will evaluate the hazard. So let's identify now for cooked rice. And this is how you can do it, and you can copy this table. All right. So you create a table of 4 columns. On your right, you have process step, then followed by potential hazard column, then the category column, and then the source column. All right. So now the process step number one, we have receiving the raw rice. The raw rice, when we receive the raw rice here, we have potential hazard is Bacillus cereus spores. Bacillus cereus spores is biological hazard that is natural contamination of rice. So this is our first potential hazard. And also during receiving, we have stones as potential hazards and insects on the raw rice. Okay? And those are physical hazards as a category, and the source is the field contamination. Thirdly, we have storage, the process step of storage, dry storage of the rice, the raw rice. The potential hazard here, we have mycotoxins and during the storage, and those are chemical hazards. And the source of such hazards is the mold growth if the moisture is present. That's why they tell you keep it in dry and clean area, because if there is excess moisture, it can support the growth of the mold. All right, if the moisture is present. And then we have washing process step. Washing, the potential hazard here would be metal fragments from the equipment wear or when equipment break down or old or pieces from the washing equipment. That's the source. These are the physical hazard as a category. Then after washing, we have cooking step. In cooking step, potential hazard here, in case we undercook, we have the potential survival of B series spores. All right. We said in the receiving raw material, we have B series spores as the natural contamination of rice. So now here, if we undercook, the B series spores could survive, and that's the potential hazard in cooking. And this is a biological hazard, and the source is inadequate cooking, of course. Then we have cooling after cooking. During cooling, again, the B series could grow here, the growth of B series during cooling, and is a biological hazard. And the reason it could grow here, the source, when slow cooking, uh, will allow the germination. So we have rapid cooking, right? And we will define it now how to do the cooking to prevent the germination of B series growth. Okay? So we have cooling. B series growth again is a biological potential hazard on this process step. And then we have the other process step is the hot holding. During hot holding, the hazard here also be serious toxin formation. The toxin could form here, and this is a biological hazard by category, and the source is the temperature abuse. During hot holding, the be serious toxin formation. Then the final step, the packaging process step, the hazard here, potentially we have hair from the personnel and jewelry. That's why we have policy, for the hair and urinary. Those are physical hazards and the contamination from personnel. So we need to control that. All right. This is for this step, okay? For the step 6, which is correspondent to principle 1, is to conduct hazard analysis. So now we have identified the hazard. Next, we are going now to evaluate the hazard, okay? So you can use this table for your hazard identification. All right, table with 4 columns. Okay, and the tool I want you to take to more, of course, is to have a checklist for comprehensive hazard identification by hazard category and process steps. All right, step 6 again, we are continuing now with the principle number 1, which is to conduct hazard analysis. Now we will evaluate. So after we have identified, now we need to evaluate. All right. All right. Now, what this step requires us, we now for each identified hazard, we need to determine if it requires control in the hazard plan or not. Okay. So here we have 2 questions that will help us always to evaluate Take note of these two questions and you can always use them for evaluation of your hazard, all right? The first question, is this hazard likely to occur? Answer to this question will help you with evaluation. And the answer will be driven from historical data, like did it happen before, or from scientific literature, of course, that which will tell you, is it known to happen in this process, or from process condition also. Does your environment support it? The answer to this question will lead you to question two. Question two here, if it occur, all right, if the hazard occur, will it cause unacceptable health risk? All right. And here the answer must be synonymous to the severity, like severity, and also identify the vulnerable population and the dose response. So if it happen, does it cause unacceptable hazard, unacceptable health risk? What is the severity? Will people be hospitalized or are they going to die? And also for vulnerable populations, you have children, elderly, and immunocompromised. And you have the dose response also. Different people, different health issues have different capacity of the dose that could cause illness. All right. Now the decision logic here, first, if both answers are yes, then the hazard requires control here. If one of the answers is no, then the hazard does not require control in hazard plan, and you may control it by prerequisite programs. All right. Let me demonstrate with the real world example of hazard evaluation for cooked rice. Okay. We are continuing with the previous example, but now we are evaluating. Previously, we have identified. Now, the hazard that we have identified earlier was B series spores in raw rice, right, as a natural contaminant. Now, the likelihood to occur, is it likely to be available in the rice? And the answer is yes, it's a naturally present in the rice. So, how significant is it? What will happen? It's not significant because the spores don't cause illness. So, in that case, now you have one answer as yes and the other answer is no. So, it doesn't require the control here. Then you move to the second hazard, which is the B series growth during the cooling. That's the raw rice now during the cooling. Is it likely to occur, the growth of B series? And the answer is yes, because if cooling is slow, if it doesn't happen as per the defined criteria, which we will explore later now, then the growth could happen. So the answer is yes. Okay, if the growth happened during the cooling, is it significant? Could it cause unacceptable health risk? And the answer is yes, because the serious growth during cooling could cause vomiting and diarrhea. And we don't want you to have diarrhea, okay? So the answer is yes. And the required control here is yes. Because you have two yeses here now. So yes, this is a required control and this is a CCP. So now you can see we have identified our first CCP as the cooling, okay? Cooling now is our CCP. So we have to make sure that the B series growth doesn't happen during the cooling. Then we move to our next hazard, which is B series toxin in hot held rice. When you keep the hot rice, does B series toxin happen during that time? And the answer is yes, if the temperature drops below 60 degrees Celsius. Well, how significant, how dangerous is it? If it happened, it will resist the heat because it's heat is stable toxin. So now you have two answers as yes, and here it requires control. That means this is our second CCP. It requires control. and during the hot hill rise. All right. Then we move to our next hazard, the potential hazard of stones in raw rice. Is it likely to find a stone in raw rice? Yes, it's possible. Well, how significant? Although you have the sieving and the cleaning and all that, how significant? It's possible to happen, but if it happened, it could cause dental injury and choking. So it's significant. It could cause unacceptable health risk. And for that reason, yes, we require control here. All right. Then we move to the other hazard, which is metal from equipment. In case of fragments from the equipment, the cleaning equipment and sieving and all that, is it likely to happen to find uh, metal fragments? It's unlikely because you have maintenance, your prerequisite program, for example, you have a strong prerequisite program. But now, if you have a prerequisite program, how significant in case it happen? It's dangerous because it could cause injury if they find metal fragments in rice, okay, in cooked rice. So now this requires controls, and for that reason, you need to install metal detector, okay. Now, this is how you do your hazard evaluation. Following the analysis, you evaluate using a table of 4 columns, one column for hazard, the second column for likelihood to happen, third column is the significance, and the fourth column is the required control. Now, in order to implement the best of the world, and I know you are one of the best, so to implement the best practices, the world class practices for hazard evaluation, you use quantitative data when available, not just yes and no. And also, you document the reasoning for each decision, and you involve microbiologists for biological hazard evaluation, and you review scientific literature for emerging hazards, and you consider worst case scenarios and not just the typical conditions, right? Those are the best practices, and I know you can do that. You can include it. The common mistakes to avoid: listing every possible hazard without evaluation, that is a mistake to avoid, and assuming that it hasn't happened here, so it means it won't happen, that's a mistake to avoid, and ignoring hazards because they are controlled by GMP, that's also another mistake to avoid. All right. The tools you can use tomorrow: hazard evaluation metrics with decision tree and documentation. This is a tool you can use tomorrow. All right. Now that's principle one, step 6. Now let's go to principle 2, step 7. All right. Just give me a second. Now, the step 7 is to determine the critical control point, CCP. All right. So what this step requires? It requires to identify the specific points, the steps, or procedures where controls can be applied to prevent, eliminate, or reduce a food safety hazards to an acceptable level. All right. So step number 7 requires you to determine the critical control points, CCP, and this is major step. Now, what is CCP? CCP is a critical control point. That is a step where you control Your control here is essential to prevent or eliminate a hazard, and also this is where the loss of control would result in an unacceptable risk, and this is where no subsequent steps that will eliminate the hazards. Those are the CCP's characteristics. So here, if we use the CCP decision tree here, you need to use these 4 questions, all right? So you start from the bottom question, Q1, preventative measure. Are controls present at this step here? All right, and then you move to the next question. For the design reduce, is this step specifically reduce hazards? If no, then you move to question number 3, the containment or contamination risk. Would hazard increase here at this step? And then also you include question 4, the later step. Are there subsequent steps to eliminate the hazards? All right, so use this decision tree. Now let me demonstrate to you with example. At the CCP, all right, just let me demonstrate to you how to determine CCP with a real world example, the pasteurization milk. All right, pasteurized milk. In pasteurized milk, now let me walk you step by step CCP analysis. So step 1, you have receiving raw milk, all right, in pasteurized milk. Step 1 is receiving the raw milk. The hazard here during the receiving, you have pathogenic bacteria such as Salmonella, E. coli, and Listeria. So you start with question 1 from the decision tree there. Are control measures exist on this step? And the answer here is yes. Supplier certification of analysis and also the testing results we demand during the receiving. So we have the control here. Well, we move then to the second question. Is this receiving step designed to eliminate the hazard? And the answer is no. The receiving is not, we did not design the receiving to eliminate the hazard. Then we move to question number 3. Could contamination occur here during receiving? And the answer is yes. The raw milk naturally contains pathogens. So the contamination could happen here. Then we move to the subsequent step. Are there subsequent steps after receiving? Are we going to do something to eliminate the hazards? And the answer is yes. We have pasteurization step to pasteurize the milks to kill the pathogens. So we have a subsequent step to eliminate the hazard. So here we will make the decision that receiving is not a CCP because the hazard will be controlled later on by the pasteurization. All right. Then we move to, give me a second, just give me a second. All right. All right, so we determined that the receiving is not a CCP. So now we move to second step, which is pasteurization. We do the pasteurization at 72 degrees Celsius for 15 seconds. That's how we pasteurize the milk, based on scientific, of course, and we will demonstrate how we calculate these numbers later on. So during the pasteurization here, we start with hazard. What is the hazard here? We have the hazard of survival of pathogenic bacteria in case we didn't meet the minimum heat and uh, the minimum temperature and the minimum time resident. The potential hazard here, that means the pathogenic bacteria could survive. So that's the potential hazard in pasteurization. So if we have that potential hazard of survival of the pathogenic bacteria, then we start with question 1. Do we have control measures here? during the pasteurization, and we said yes, we have time temperature controls. That means we need to heat the milk for 15 seconds at 72 degrees Celsius to control the survival of, to eliminate the survival of pathogenic bacteria. So then we move to question 2. Is this a step designed to eliminate the hazard? And the answer is yes. So now you have two yeses. So now, because we have two yeses, we determine this is our decision, our CCP number 1 for biological hazards control. All right. Then we move to step number 3, which is step 1 was receiving, step 2 was pasteurization. Now the step 3 is filling the milk into the cups. So now during the filling here, we start with the potential hazard, and we have post-pasteurization contamination with listeria. That's the hazard in filling the milk into the cups. So we start with question 1. Do we have control measures here? And the answer is yes. We have sanitization. Okay. We have sanitation. And we have environmental monitoring here. Then we move to the next question. Did we design the sanitation and the environmental monitoring? And did we design the filling step to eliminate the hazard? And the answer, no. The filling step was not designed to eliminate hazard. It was designed to fill the milk in the cups. All right. Now, the third question then would be, could contamination occur here during filling? And the answer is yes. So the subsequent question, the next question will be, do we have subsequent step, the next step to eliminate the hazard after we fill it in the cups or into bottles? And the answer is no. It will be ready to drink. People will go to supermarket, buy the milk and drink it. So they will not heat it up. So this is ready to eat, and we don't have kill step. So here we determine the decision that we have two no's here and two yeses. So this is a CCP, right? But for biological, or we control it by robust prerequisite programs, and we will demonstrate how to do that. In case you want to implement the best practices in the world here of determining the CCP, that means first you limit the CCP to truly critical steps. You don't, and usually should not be more than 5. And also you don't make every step CCP, you dilute the focus, and you implement strong prerequisite programs to reduce the need for CCP, and you document why steps are not CCPs to show thorough analysis. Those are the best practices in the world so that you can implement. All right. Another tool I want you to take with you to implement tomorrow in your organization: create a flow chart for CCP decision tree and CCP determination worksheet. All right. Now, let's go through examples of CCPs, the common CCPs across food industries, and you will find a couple of examples here that you could reflect on your CCPs and see the improvement you need. So while every HACCP plan is unique, certain CCPs appear repeatedly across industries where I found, and understanding these patterns will help you identify the CCP in your own process, okay? So first, we have the thermal processing CCPs, which is most common. And in thermal processing CCP, we have cooking or pasteurization. And the products that use this cooking or pasteurization as CCP, you have meat, you have poultry, you have seafood, you have dairy, and you have juice, and you have egg. All these products use cooking or pasteurization as the CCP. The hazards that are controlled through pasteurization or cooking include pathogenic bacteria such as Salmonella, Listeria, and E. coli. And the critical limits here usually is time plus temperature combination. All right, like what we said before, 72 degrees for 15 seconds. Okay, An example here is chicken breast is cooked to 74 degrees for internal temperature. Okay, internal, not external temperature, internal temperature. The other thermal process CCP, you have retort or canning, and the products that use retort or canning as the CCP includes canned vegetables and soups and food and pet foods. Wait, all right. And the hazards control with retort or canning include C. botulinum spores, and the critical limits here you have F0 values into time at 221 degrees Celsius for or equivalent. Example will be low acid canned food with where F value is equivalent to 3 minutes at a minimum. All right. Now the second type of CCP, you have cooling CCP through rapid cooling. The products that use rapid cooling as CCP, you have cooked rice and pasta and soups and sauces. The hazards that are controlled uh, with cooling, you have the hazard that are controlled with rapid cooling. You have Bacillus cereus, Clostridium perfringens growth. Okay, and the critical limits you have 60 degrees Celsius to 21 degrees Celsius in 2 hours, and then from 21 degrees Celsius to 5 degrees Celsius in 4 hours. Example is cooked rice is cooled from 90 degrees Celsius to 5 degrees Celsius within 6 hours in total. So cooling is another type of CCP. And then you have metal detection as another type of CCP. Okay. The metal detections here, the products that are controlled through metal detection include ground meat, bakery products, and processed food. Just wait. The hazards that are controlled with metal detector, including metal fragments, which are physical hazards. The critical limits usually is set at ferrous are set at 2.0 uh, mm, non-ferrous are set at 2.5 mm, and stainless steel are set at 3.0 mm. Examples will be ground beef passed through metal detector before packing. We will demonstrate further, don't worry. The other type of CCP is pH control CCPs. And this is used for acidifications. And the products that use pH controls include pickles and fermented vegetables and acidified sauces. The hazards that are controlled here, including C. botulinum growth, which requires above which requires pH above 4.6, and the critical limits here are set. pH is set to be below 4.6 or pH to be set below 4.0 for certain products. Example would be pickled cucumber acidified to pH 4.2. The other type of CCP, you have water activity control CCP, and is used for drying or dehydration. And the products that use water activity as CCP include dried fruits, jerky, and powdered ingredients. And the hazards that are controlled with water activities include microbiological growth, such as bacteria, mold, and yeast. And the critical limits here are said water activity is said to be uh, less than 0.85 for most bacteria, and water activity is set at less than 0.60 for molds. Example would be beef jerky dried to water activity at 0.75. Then the other type, you have chemical controls, CCPs also for allergen control at rework. The products that use chemical controls as CCP are multi-allergen facilities. The hazard controls here include undeclared allergens, and the critical limits here is that the rework will only be added to the same product or uh, same products or products with the same allergen declaration. Example will be peanut containing rework will never to be added to peanut-free products. For world-class insight, the best HACCP plans have few CCPs, like we said, between 1 to 5, because they have strong prerequisite programs handling routine controls, and CCPs should be reserved for hazards that absolutely require monitoring and documentation at the specific steps. All right. Now let's move to step number 8, which is correspondent to principle number 3. In step number 8, it requires you to establish critical limits. All right. So what this step requires, it requires us to set maximum or minimum values to which biological, chemical, or physical parameters must be controlled at the CCP to prevent, to eliminate, or to reduce the hazards to an acceptable level. So what makes the critical limits valid here? First, the critical limit must be measurable and can be monitored in real time or near real time. Critical limit also must be science-based in order to be valid and is driven from regulations, scientific literature, or experimental studies. And also the critical limits will be valid if it's achievable with your process can consistently meet them, and CCP is valid when it's validated and is proven to control the hazard. Those are the elements that make your critical limits valid. Must be measurable, scientific based, and achievable, and also validated. The type of critical limits. First, you have the time temperature limits. Time temperature limits is most common for biological hazard controls. Example is 72 um, cooking to 74 degrees Celsius for 15 seconds of poultry cooking. And also you have pH is for acid or acidified foods. Example will be pH set at 4.6 to prevent C. botulinum or botulinum. And then you have the other type of critical limits is water activities, is for dried or concentrated products. Example will be water activity set below 0.85 to prevent bacteria growth. And then you have concentration is another type of critical limits for chemicals preservations or for sanitizers. Example will be 200 ppm chlorines in wash water. And then you have physical parameters, another type of critical limits, such as size, weight, and dimensions. Example would be metal detector sensitivity set at 2.0 mm Faros. And then you have also the sensory, which is rare, is only used when no objective measure exists as a critical limits. Example will be visual inspection for glass with defined criteria, of course. Those are the type of the critical limits. Now, let's look at the real world examples for critical limits for pasteurized orange juice. Okay, for pasteurized orange juice. So the CCP here is pasteurization. The hazard, potential hazard here is pathogenic bacteria, E. coli 0157, H7, and Salmonella. And the critical limits options here, all which are all scientifically proven. So we have options based on science to set the critical limits. Okay. The first option is to set the critical limit at 71.7 degrees Celsius for 15 seconds, which is ATST or high temperature short time, or set a critical limit at 88 degrees Celsius for 1 second, which is higher heat and shorter time, or set critical limits at 94 degrees Celsius for 0 0.5 seconds, which is an ultra high temperature and short time. All right, those Those are all scientifically proven. But we selected the critical limits of 90 degrees Celsius for 15 seconds. Now you might ask, why did we select something different out of these options? Well, we select this reason because it provides safety margins above the minimum requirements. All right? Instead of 71.7 degrees Celsius for 15 seconds, we raise the temperature to 90 degrees Celsius for 15 seconds to provide safety margins. The safety margin here you have around 18 degrees Celsius above. All right? Now, this is not the random selection. This is a regulatory basis from FDA juice HACCP regulations 21 CFR 120. And the scientific base for this selection also, it achieves 5-log reduction of target pathogens. All right, 9 degrees Celsius for 15 seconds in pasteurized juice achieve 5 logs reduction of target pathogens. Okay, then we look at the monitoring parameters here. How will we monitor that? The temperature, we will set it at a minimum of 90 degrees Celsius, and we will measure it continuously, automated. And the time, we will set it at a minimum for 15 seconds. It's calculated from the flow rate. And the flow rate setting will be set it at a maximum of 5,000 liters per hour to ensure the resident time is achieving 15 seconds. All right, that's the monitoring parameter. And then for critical limits versus the operational limits, all right, now you need to pay attention here. Not only critical limit, not just 90 degrees Celsius for 15 seconds, you have to have operational limit also. Now, first, the critical limits here, as per the regulatory boundary with the sign base that we show you, is 90 degrees Celsius minimum. And if violated, that means the product is unsafe and it requires corrective actions and documentations. So we set the operating limits here, internal target, we set it at 92 degrees Celsius to provide buffer before critical limits is reached. And this allows the adjustment before the safety is compromised. All right? Now, if we look at the world-class practices, you set the operation limits at 1 to 2 standard deviations from the critical limits. What we just did there now, we set at 92 instead of 90. That's the world best operation procedures process, and you can apply. And also in the best practices, they use multiple parameters when possible, temperature and time. And also they document the scientific sources for every critical limits, and the review and update critical limits when new science emerge. So now you can also use that, all right? The common mistakes to avoid is using vague limits like we will cook it until done. Cook it until done. That's vague. Avoid that, okay? And then also setting limits without scientific justification. Nah, you need scientific justification. All right? And then also the other mistake is confusing quality limits with safety limits. Avoid that too. And making limits so tight that they are impossible to achieve. Don't do that, all right? Avoid these mistakes. And the tools I want you to take home with you and tomorrow take it to work is to create a template for critical limits validation with scientific reference documentation. And you can do it, you can validate your critical limits same way. All right? You can establish your critical limits this way with this demonstration of the pasteurized orange juice. Use the same examples, all right? Take notes and do it. I know you can do that. That is step 8. It's finished. Now let's move to step 9, which is correspondent to principle 4. All right, let me sip water. Now, the step 9, which is correspondent to principle 4, is to establish monitoring procedure. All right? So what this step requires to establish monitoring procedures, you need to define the procedure to measure or observe the critical limits at each CCP to ensure they remain under control. All right. All right. So why did this step matter of establishing monitoring procedure? Monitoring is your early warning, okay? And it detects loss of control before unsafe product is produced. Without monitoring, you will not know what's happening. So you need to monitor what's going on, all right, consistently. And the frequency is determined by the level of risk and the operations. We will demonstrate that shortly. Now, the four key questions here for monitoring. First, you ask the question, what will be monitored? Okay, the specific parameters. Are you going to monitor the temperature? Are you going to monitor the pH? Are you going to monitor the time? Are you going to monitor the metal detector? Are you going to monitor the sanitation? All right, the cleaning. You just have to determine first. Secondly, how will it be monitored? The methods and equipment. Do you need thermometer, pH meter, metal detector, visual inspection, ATP test? What kind of the method do you need to test? And then the third question is how often the frequency. Do you want to monitor continuously, every batch, every hours, every minute? Then the fourth question is who will conduct the monitoring? The specific job, not the person, the specific job. Is it the operator, the supervisor, the manager, the QC personnel? All right. And they must be trained. Now, these are the type of monitoring that can guide you to enhance your monitoring procedure. First, you have continuous monitoring, which is preferred, is conducted through, and we are talking here about CCP monitoring, okay? CCP monitoring. The continuous monitoring first is preferred because it utilizes the automated sensors with records, all right, with recording. It automates the monitoring and recording, all automated. And then you have the sample. The example here will be chart recorder on pasteurizer measuring temperature every second. That will be your example. And the advantage of having continuous monitoring is it's immediate. It immediately detect, and also you have complete records without human errors. So that's the advantage of having um, continuous monitoring. The second type of monitoring is intermittent monitoring, and this is conducted periodic checking at defined intervals, like hourly, 30 minutes, 20 minutes. The example will be pH parameters, pH measurement every 30 seconds or every 30 minutes during the acidification. The advantage here, intermittent monitoring is practical when continuous monitoring is not feasible. All right? There are instances or there are controls that you cannot implement the automated monitoring. The third type of monitoring is batch monitoring, once per batch or per bag or per lot. Example will be metal detector of every case before shipping. So you place a metal detector and the product will pass through it. All right. And the advantage is having 100% inspection of discrete units. Those are the three types of the monitoring. Now let me demonstrate with the real world the monitoring for chicken cooking CCP. All right. How do you monitor the CCP in chicken cooking? And this is going to be good for the people in restaurant and food service. Now, this the CCP here is cooking chicken breasts. Okay. And the hazard here is survival of salmonella is the potential hazard. During the cooking, you can undercook and the salmonella could survive. That's the potential hazard. And we set the critical limits here, temperature to be maintained above 74 degrees Celsius, at the minimum of 74 degrees Celsius. Okay. the minimum. And the monitoring procedures here for this CCP, what are we going to monitor first? We are going to monitor the internal temperature of the chicken breast, the thickest part. So we are not monitoring the external part. We are monitoring the internal part of the chicken breast and on the thickest part. And how are we going to do that? We will do it through calibrated digital probe thermometer that is calibrated at plus or minus zero point 0.5 accuracy. And how often, the frequency, we will do it every 30 seconds or every 30 minutes during the production, plus on the first chicken breast and on the last piece of each batch. And who is going to do that? Of course, is a line supervisor who is trained in proper thermometer use and calibration also. And the recording required here, we require temperature recorded on CCP monitoring log with time and product codes and the initials of the supervisor. Well, what are the equipment requirements here to conduct this? We need thermometer that is calibrated daily using ice water. I will demonstrate earlier. And this is an easy calibration way, doing it daily on ice water to set the thermometer at 0 degrees Celsius and boiling water at 100 degrees Celsius. And the backup thermometers also need to be available, and the thermometer need to be sanitized between the use. So you don't stick it in one breast and move it to the other. You sanitize it, all right, between the interval times. These are the monitoring equipment characteristics that will be effective equipment. The first characteristic is the equipment need to be accurate, need to be calibrated regularly with known standard against known standards, and must be accurate, appropriate for the critical limits. The equipment also need to be precise with repeatable measurements with the minimum variation between the readings, and the equipment need to be rapid to provide the results quickly enough to take corrective actions, and with the real time or near real time is preferred. And then the equipment need to be reliable to function consistently in the production environment, and we need backup equipment to be available. All right. For the best practices in the world, they automate the monitoring whenever possible to reduce the human error. So you identify in your processes whatever need to be automated is better to be automated so that you can have complete documents and you will never have human errors. And secondly, in the best practices, they use continuous monitoring with alarm for critical CCPs. And also, they calibrate all the monitoring equipments on documented schedule, and they train the monitors thoroughly. Okay, people who monitors, they train them thoroughly, and they are your first line of defense. So you make sure they are competent, and you also in the best practices in the world, they make monitoring procedures simple and clear, one page at the maximum. You don't need to complicate it. And also in the best practices, they position the monitoring equipment for easy access and visible. You don't hide them in office and you need permission to access them. No, you put them in accessible areas. The common mistakes to avoid here is when monitoring too infrequent to catch a deviation, okay? And also using uncalibrated equipment and assigning monitoring to untrained personnel and making procedures so complex they are not even followed, and monitoring quality parameters instead of safety parameters. All right, the tools you can use tomorrow here is CCP monitoring procedures templates and equipment calibration log. You can create that and you can use them. All right, let's look at monitoring examples here, which you can find few of them to replicate in your organization. Those are the real world monitoring procedures, and those are the complete examples across different CCPs. First, you have pasteurization CCP in dairy, milk. The critical limits here is set at 72 degrees Celsius for 15-second minimum precedent time. And the monitoring procedures here, What are we going to monitor? We will monitor the temperature at holding tube outlet. And how are we going to measure that? We will monitor with continuous recording thermometer, RTD sensor with chart recorder. How often? The frequency will be continuous and is recorded every second, automated. And who is going to monitor the chart recorder is the pasteurizer operator will monitors the chart, and the QA personnel will review the charts daily. And the recording requires here automated charts is recorded automatically, plus operator initials charts every hour. So they need to sign every hour to confirm the intactness. And then the alarm is set to be audible alarm if the temperature drop below 72 degrees Celsius. Alarm will be activated, and the corrective actions here trigger any reading below 72 degrees Celsius. It will trigger automatic flow diversion valve. That means if the temperature dropped below 72, the automatic machine will take the milk to a different tank and keep it on hold there. It will not flow to the filling and finished product. Automatically, it will divert and the line will stop. Okay? Then the second example, you have cooling CCP in food service. Here we have cooked rice. The critical limits here is set at 60 degrees Celsius to cook to the rapid cooling from 60 degrees Celsius to 21 degrees Celsius in 2 hours, and then from 21 degrees Celsius to 5 degrees Celsius in 4 hours. This is the cooling of the CCP of cooked rice. The monitoring procedures here, what are we going to monitor? We will monitor the internal temperature of the rice in cooling container. How are we going to do that? We will do it through a calibrated probe thermometer. We will insert it into the center of the product. And how often? The frequency. We will do it at the start of the cooling and 2 hours, and also 4 hours and 6 hours. And who is going to do it is a kitchen supervisor or designated trained staff. And the recording here will be time temperature locked with batch ID and start time and all the readings. And the visual aids here, we will need cooling charts posted at cooling station showing acceptable temperature range. Now this is the CCP, all right, for the cooked rice. Another example will be the metal detector or metal detection CCP process in the processing facility. The critical limit here for metal detection is set at the ferrous is set at 2.0 mm, non-ferrous set at 2.5 mm, the stainless steel is set at 3.0 mm, and the monitoring procedures here, what are we going to monitor? We will monitor the metal detector sensitivity and reject mechanism function. How are we going to do that? We will pass the test pieces through the detector, including the ferrous and non-ferrous and stainless at critical limit size each. We will pass it through the detector. How often are we going to do that? The frequency. We will first do the passing at the start of the production. Then every hour we will do the passing test during the production. And then after any 15-minute stoppage, more than 15 minutes, we will also do the passing. And at the end of the production, we will do the passing test. And who is going to conduct that is operational, the line operator, who is trained in metal detector operations. The requiring recording here, we have metal detector tests, test log with date and time and test results, and we'll have pass fail for each metal type and operator initials. The verification here, including the rejected products, physically will be separated and counted to match the reject counts. All right. Then we have another example is pH control CCP in acidified foods. And now here we have salsa as an example type of pH. And in salsa acidified foods facility, we set the critical limits. pH must be below 4.6 or must be maintained below 4.2. The monitoring procedures here. What are we going to monitor? We will be monitoring pH of finished salsa. How are we going to do that? We will do it through calibrated pH meters with 2 points calibrated with pH 4.0 and at 7.0 buffer. The frequency, we will do it every batch and the minimum 3 readings per batch from the different locations. Who is going to do it is QC technicians who is trained in pH meter use and calibrations. And the recording here will be pH log with batch number and the time and all the pH readings and average pH and also the technician signature. The calibrations here, the pH meter is calibrated at the start of the shift and every 4 hours, right? Then we have the fifth type of the CCP is water activity CCP in dried products, beef jerk, all right? And the critical limits here is set the water activity is set to be below 0.8, uh, 0.85. And the monitoring procedures here, what are we going to monitor? We will be monitoring water activity of dried jerky. How often? We will be monitoring the water activities. How are we going to do it? We will be mm, um, measuring water activities with calibrated, which is calibrated with salt standards. We'll use the water activity meter, which is calibrated with salt standards. How often? The frequency. We will do 3 samples per batch at the beginning of the batch, at the middle of the batch, at the end of drying cycle also. And who is going to conduct the testing is the production supervisor or QC technicians who are trained. And the recording requirements here, we have to record the water activity log with batch ID and also sample locations and water activity readings and signature and also the whole products. And we held until water activities results confirmed at to be below 0.85. All right. Those are the type of the CCPs that you can see, and you can control that the same similar way. You can replicate in your organization. Now, let's look at the key monitoring principles that we have demonstrated with our examples here. First, we have demonstrated that it must be specific and measurable parameters. That's the first principle. Also, is defined. We have defined frequency appropriate to the risk and identified responsible personnel and also clear record requirements and equipment calibration specified and immediate corrective actions trigger defined. Those are the monitoring principles that can drive your design. Okay, so take a note of these principles and implement whenever possible. All right. Now let's look at the world-class trend analysis addition. In the world-class best practices, you add trend analysis. Okay, you need to add trend analysis in your monitoring, and don't just record. You need to analyze the trend. Why? You First, the reason you need the trend, they show you the direction. So every day, small deviations, even if you are still within the safe limits, it's showing you that you need to do something about it. All right. So you need to plot the monitoring data on a weekly basis, then identify the patterns approaching the critical limits, then adjust process proactively before the deviation occur. And for example, for that will be if pasteurization temperature is trending down over days, you can schedule the equipment maintenance before the critical limit is violated, right? So you can see now it's beneficial. You can do that world class practices. Take a note and add the trend analysis and thank yourself later. All right. That's the step 9. Now let's move to step 10, which is correspondent to principle 5. And step 10 require us to establish corrective actions. This is one of my favorite steps. To establish the corrective actions. All right. Give me a second. Now, Let's look at the step 10 here, which is corresponding to principle 5 to establish the corrective actions. What this step requires, it requires to define the specific actions to be taken when monitoring indicates a deviation from a critical limits. This simply say that you need to define, okay, and to plan in case of deviation. In case your temperature went below the limits, what are you supposed to do? So in the best practices, you define that in advance, right? You define in case of deviations, for example, the valve will divert to whole tank, the production will stop, the maintenance will be called, and we will go through it, and the corrective action will be done, and the sample will be taken by the QC for the affected product, and then do the analysis and determine the outcome. That's simply what it means here. All right. And why it matter? It matter here when control is lost, you must act immediately, right? Whenever you lose the control, you need immediate action to prevent unsafe product from reaching the consumer, and also to correct the cause of the deviation so that the production can continue, and to prevent the recurrence. So that's why we need to define the control measures, okay? Corrective actions. We need to define the corrective actions. The pre-planned corrective action is my favorite. All right. Now, the three components of the components of the corrective actions, these are very critical, and you can just replicate them. This will make your life easier. First is the components is the control to control the product. This is the first thing you need to do for corrective action is to control the product, to identify all affected product, then segregate and hold it, and evaluate the safety, and make a disposition decision to either release, reprocess, or destroy. This is the first component. And when you do them structurally like this, three, your life will become easier. Second, once you have hold the product, now you need to correct the deviation. All right? You need to identify the cause and fix the immediate problems and restore the control at the CCP. Easy as that, right? The affected product, you kept it on hold, you segregated, and you evaluate. The sample was taken to QC for check or the inspection, and then you will make the decision based on that. So now, once that happened, now you need to work with the production and the maintenance and relevant departments to identify the root cause. What happened? Why did this failure happen? So that you can fix it, fix the problem, and restore the control as a CCP. All these things must be done within 30 minutes or 1 to 2 hours. The third component of the corrective actions is to prevent the recurrence. This is the important part here. Problem doesn't have the system. We are learning from system every day. So when the problem happen, it doesn't have to repeat. You just have to learn from it and do the next one. So now here, to prevent the recurrence, we need to determine the root cause, right? Once we figure out the root cause, then we need to prevent the preventive measures. So if the root cause, for example, let's say uh, the temperature dropped for pasteurization, and the reason is that, for example, you have the interface problem. So now you need to relocate. Maybe the position of the location of the CCP need to be relocated. If you leave it there, the interface problem also will keep happening. So you just relocate, and now it will never happen for the same reason. So you need to determine the root cause first. So then you can implement the preventive measure. And then you modify the procedure if you need that. For example, relocation of the CCP, and retain the personnel if needed. Retrain the operation. If you relocate the magnets or the temperature, the CCP, then you need to retrain the operator. Maybe you put it in a location where you have a different operator also. Now let me demonstrate with a real world example the corrective action for pasteurization deviation. All right? For pasteurization deviation. Now the deviation that is detected here is the pasteurizer temperature dropped to below 70 degrees Celsius for 3 minutes. and the critical limits is 72 degrees Celsius at the minimum. All right. So now here, the immediate corrective actions we need to do. First, we need to control the product. You remember the three components, right? We need to stop the product. Uh, uh, we need to control the product, sorry. Step one is to control the product within 5 minutes. All right. So how are we going to do that? We have installed the automated flow diversion valve that is activated when the temperature drop below the limit for 5 minutes. The automatic flow diversion is activated and will automatically divert the flow of the milk to a different whole tank and will pour the product there in a whole tank, holding tank. Okay. Secondly, once that happened and the alarm is triggered, and so you see how it works, the alarm also is set. So the alarm will be triggered, it will go on, the valve will automatically divert the milk to the tank that we dedicated for the on-hold product. And then also the system automatically will send text message to QC and also to the production manager and to operation manager. And we learned this in previous modules, how to design this system, the escalation also, hierarchy, right? So now the system will send the text message, will alert the QC manager, the production manager, and the maintenance manager, and it will divert automatically the milk to the holding tank. So now these three head of departments will come, put the tag on the tank. This product is on hold, do not use, will be put on the tank. The operator will do that while the managers are coming, and the product also, the production will now automatically stop. And then we will identify the affected products, and mainly is done through the operations and maintenance, and also with the involvement of QC. Now the product also has a stop automatically, so they need to figure out what happened, and all the affected product now has been identified there, and we have all the mix. The milk must be all the mix that the milk that process between 10:15 to 10:18 based on the flow rate, because the deviation happened for 3 minutes. So those are the affected product which have been diverted already. All right. And the volume affected is 250 liters. And the product ID, batch number 2024-0124-A. All right. That's the first, you control the product. Secondly, now you correct the deviation within 30 minutes. So what happened? The maintenance now immediately came, either call or came through the tax, and then the cause was identified, and the reason is the steam valve partially closed due to scale build up. So that's the root cause here. So what happened? The steam valve now is clean and tested. All right. And then the temperature is restored to 74 degrees Celsius and is stabilized for 15 minutes. And then the test is run. The test run is conducted with water, not the milk, with water to verify the control first, and then the production resume at 10:45. All happen within 30 minutes. Now, step three: once the production resumption happen, now you need to evaluate the affected product within 2 hours. The product that is on hold. So the option one is to evaluate and reprocess through the pasteurizer, which is eventually selected this option. So the 250 liters were repasteurized at 74 degrees Celsius for 15 seconds and sampled for to test the pathogens in QC, and it was negative. And then the product was released after the verification. And we had option B to destroy the product if the reprocessing was not feasible. Then now, after releasing the product and the production is resumed now, you need to prevent the recurrence within 24 hours. So what happened? The root cause here, Preventive maintenance schedule was inadequate. There was a gap. The preventive maintenance between now and the next preventive maintenance, there is a gap. So it happened that the build up of on the valve instead of cleaning happened because there is a big gap of preventive maintenance. So to correct that, the corrective action is to increase the steam valve inspection from monthly to weekly to increase the frequency, right? And now the procedure also need to be updated to add the valve check to daily startup checklist. So when the operator is coming to start, they need to check the valve for the cleaning. That is clean and confirm. If there is any issue, they need to contact the maintenance, even if before the week happen. Now, the operator now is retrained on daily warning signs, okay, and the temperature trending downward also. The operator is retrained now in case they see the daily, the small trends, even if we are still within the limits, they need to contact the QC and the maintenance and the manager, you know, depending on how the the procedure will go. So now the documentations you need here is corrective actions report must be completed and it must include deviation details, product dispositions, and the root cause and preventive measures. And the reviews and signed by QA manager also, and is filed with HACCP records. All right, that's that. Now the corrective action decision tree that you can use. You can use that example or you can use this one here also. It's just like us. Is the product safe? The initial safety check. And then you release with documentation and approve and record. Or you reprocess and verify corrective actions. See that is good, or you destroy, you dispose with the documents. Those are the decision trees questions you can use. Now let's compare, like we said earlier, you need to have pre-planned and unplanned corrective actions. And definitely pre-plan is the best one and it's preferred. The pre-plan corrective actions is to write down in advance for predictable deviations, which facilitate, well, like we said before, in case of the deviation by 1 degree or 2 degree for 1 minute or 2 minutes, what do we need to do? All this need to be written down and train the operator and put it there. So when that happens, they just need to follow steps. It allows faster response and also it's consistent decision making. And the example here will be if cooking temperature fall below 74 degrees Celsius, extend the cooking time per the time temperature templates, and the template will extend to include other scenarios. All right. And here, that's the plan, the pre-planned corrective actions. Now, for the unplanned corrective actions, it's for unexpected deviations, and it requires expert judgment and must still follow three component structures. All right, the three components that we talked about earlier. And the example here would be equipment failure requiring engineering assessment. All right. Now, the best practices, the world-class practices, what do? They write specific corrective actions for each CCP in advance, pre-plan for each CCP, and also they include decision metrics for common deviations. In case this happen, you need to do this. They do that, and also they empower the line personnel to take immediate actions uh, for immediate product control actions, and also they require the management review for root cause and prevention, and also they track the correct actions to identify the recurrent problems. So you see also the trend is not only in the small deviations. Trend could happen sometimes if if the recurrence problem happen at the same areas few times. When you follow the data, they will tell you in 6 months if you have 3 deviations in one equipment and have 5 or 6 equipment, 6 deviation in another equipment, and the other one have 20 deviations, that means it's telling you something, right? So that's uh, they track the corrective actions to identify the recurrent problems and apply the improvement and use the corrective actions data to improve the process. These are the best practices that you can replicate and you can become also the best, right? You can do that too. Now, the common mistakes to avoid: first, using being vague with corrective actions, like take appropriate actions. That's vague, and I've seen it in few organizations. Avoid that. And also releasing the product without proper evaluations. Avoid that. And fixing the symptoms, but not the root causes, like what happened in the above scenario. If in case like the maintenance just came, clean, and leaves, that's just the symptom. But adjusting the schedule to increase the frequency, that's the root cause, right? So avoid fixing the symptoms and leaving the root cause, and also having inadequate documentations. Avoid that risk, that mistake, and no follow up to verify the effectiveness. So the tool you can use here tomorrow: create a template for corrective action plan and corrective actions report form, and have all the pre-plan you want for all the CCPs, right? You can do that, and it will give you more consistency, peace of mind, and fast response to your deviations. Now, the corrective actions examples here. Okay, let's have real world example for corrective action scenarios. And this is a complete corrective action example across different deviations. Scenario one, we have cooking temperature deviations for chicken. The deviation here, we have chicken breast is cooked to 72 degrees Celsius instead of required 74 degrees Celsius at the minimum. The immediate action here, within 5 minutes, is to stop the production line and segregate all the chicken from the affected batch number 2024-0124-C, which are 150 pieces, and then place the tag to keep it on hold and pending for evaluation tag. And then you need to document the time of deviation, which was at 2:35 p.m., and the temperature recorded was 72 degrees Celsius, and the operator name also for the documentation. And once these are the immediate actions within 5 minutes, then for the product evaluation, you have two options. The first option is to recook, which is selected in this case. So you need to return all the 150 pieces to oven, and you need to cook to 76 degrees for internal temperature, 76 degrees Celsius, to provide safety margin instead of 74. And then you need to re-verify with calibrated thermometer piece by piece, and you need to document the new cooking time and temperature, and you need to release the product after the verification if you verify. The second option is to destroy if the product quality compromised by the recooking. Okay, so the second option stand until you make the decision with the verification. And then once you're done with that, you have the root cause analysis and you investigate. So the investigation here revealed that the oven thermostat calibration drift and the distributing factor here for this root cause is the preventive maintenance was overdue by 2 weeks. These are the root cause. So now we apply the corrective actions. And in corrective actions, we have immediate action is to recalibrate oven thermostat. And then the short-term action is to verify the calibration with independent temperature logger. And in the long term, we need to implement automated maintenance reminder system, like what we did with the pasteurizer there. And the preventive action is to add weekly oven temperature verification to the checklist. All right, those are the corrective actions. And then the documentations required here, we have corrective actions report with the number 2024-0124. This includes, the report includes the photos of hold tags and recooking records and calibration certification. And also is reviewed by the production manager and QA manager. And the follow up, we need to verify the effectiveness after 30 days to ensure the recurrence never happen. All right. That's for scenario one. All right. For the cooking temperature deviation. You can use this if you work in a restaurant or if you work in a hotel, if you work in food service industry, you can use this scenario for corrective actions. It will guide you and will make your life easier and your work smooth, and you will make sure that you preserve the safety for the consumers. Now, let's move to the second scenario, which is metal detector failure. The deviation here, the metal detector failed to reject the test piece of 2.5 mm non-ferrous at 10:15 a.m. So the immediate actions here within 2 minutes, the production line is stopped immediately, automated, and all the product produced since last successful test since 9:15 a.m. were placed on hold. Because every hour we test here, hourly, if you remember, the frequency here is hourly. So from 9:15 we test again at 10:15, and the metal detector failed to reject the piece. So any product that produced since the last test at 9:15 now is placed on hold. And the volume affected are the 45 cases, or equivalent to 1,080 units. And the metal detector was taken out of service at this point. And then once this corrective actions apply, immediate action applied, now we move to product evaluation. In product evaluation, all the 45 cases will be re-inspected through backup metal detector, and the results, we didn't find any metal detect we didn't detect any metal in any unit. And the decision here is to release the product after 100% re-inspection. Then once we evaluate the product, now we move to root cause. The root cause investigation found that the metal detector sensitivity drift due to electrical interface from nearby equipment, and the new welding equipment installed in adjacent area during the previous day. Those are the root cause for the drift. All right. So now then we move to corrective actions. After the root cause identification, the immediate action is to relocate the metal detector away from interface source. Secondly, second action is to verify the test with all the three pieces, the ferrous and non-ferrous and stainless steels, and to ensure 100% test pass. And the preventive action is to install electrical shielding. And for the procedure updates is to add the sentence, check for new equipment and interface sources. We add this sentence to the startup checklist and for every day. And then we increase the test frequency from hourly to 30 minutes for a week to confirm we are on the line. All right. This is the second scenario. You can replicate also. You can take the notes and replicate in your organization for the metal detector in case of failure. All right. But I wish you all the best. Now, for the third scenario, we have pH control deviation at seltzer. Here we have seltzer product. The deviation here, the batch pH measured in this batch, the pH measured at 4.4 instead of the required to be under 4.2. All right. So the immediate action here for this pH deviation, first, the batch number 2024-0124-S, which is 500 kilograms, placed on hold. And then we put a tag, do not fill or package, and then we investigate the cause. All right, we start the investigation. In the meantime, we conducted the product evaluation also. And in product evaluation, the pH is at 4.4, which is above the critical limit, but it's still in acidified food range, right? Below 4.6. But the risk assessment, okay, this is low risk, but it does not meet the specification regardless. So now the corrective actions here, first, which we select the first option, is to reprocess. And to reprocess, we have to add a calculated amount of citric acid to reduce pH, and also mix thoroughly for 15 minutes, and then retest pH for 5 different locations. And the results of the 5 samples from 5 different locations came out as pH at 4.0 and 4.1 and 4.1 and 4.1 and 4.0. These 5 samples are averaging at 4.06. So we made a decision to pass a release for packaging. Then we moved to the root cause investigation. We continue with the root cause investigation, and we found that the tomato supplier changed the variety already without telling us, with lower natural acidity. And as a result, acid addition formula was not adjusted for the new variety because nobody knows. So now the corrective action here, first, immediate, is to test the pH of all the incoming tomatoes, all right, with the communication. Also, to strengthen the communication, alert the suppliers to keep the communication, but nevertheless, we will test the pH for all the incoming tomatoes. That's the first immediate action. The second option is to adjust the acid addition formula based on raw material pH. And the third action is to apply preventive action, which requires pH specifications from all the tomato suppliers. So let me go back to the second option. Once we already now test every incoming um, tomato, now we update our formula, adjust the acid addition formula based on the raw material, based on the variety. So it's not static anymore. And you can see this is example of a living asset. Now, the other option, the other action that was taken, preventive action, is to require pH specification from all the tomato suppliers now. So all the suppliers have to give us their specification of the pH. And then the verification also action is to test the finished product pH for the next 10 batches. So we are not rushing, right? Now you can use also this example. It's a very beautiful example of salsa deviation, the control deviation, pH control deviation. Not necessarily the salsa, but you can use it in any deviation to have the best practices, right? Now let's have scenario 4 is cooling deviation at rice. All right. So the deviation here now, the cooked rice cooled from 60 degrees Celsius to 25 degrees Celsius in 3 hours. But that exceeds our 2 hours limits. All right. So the immediate action we need here, it we need 2 hours maximum, but it did it in 3 hours. So the immediate actions that we implemented here, first, the affected batch, which is 20 kg cooked rice, batch number 2024-0124-R, was placed on hold immediately, and the risk assessment was conducted, right? Then we move to product evaluation. The time in danger zone is from 60 degrees Celsius to 21 degrees Celsius, took 3 hours versus 1 hour versus 2 hours limits. That's too long. So we have Bacillus cereus risk here is high because the spores can germinate and produce toxin. And the decision here is to destroy the product because it cannot be made safe by reheating. As you know, the toxin is heat stable here. And then we move to the root cause, and the cooling container was too deep. That's what we found with our analysis, that the cooling container was too deep with 15 centimeters depth, and it was insufficient cooling capacity in walk-in cooler also because it was overloaded. So we applied the corrective action. First, the immediate action is to destroy the affected batch and document the destruction. Secondly, its equipment is to purchase a shallow cooling pans with a maximum of 5 centimeter depth instead of 15 centimeter depth. And then the procedure action here is to limit the batch size to ensure the proper cooling. And the training also is to retrain all the kitchen staff on cooling requirements. And then the monitoring is to add intermediate temperature check at 1 hour. And for verification, we monitor the cooling time for the next 30 days. All right. The example of cooked rice, you can use also if you use cooked rice. All right. Or any cook material or products. Now, the key lessons from these examples all first, the speed matter, if you notice, is speed matter in every example because immediate product control prevents unsafe food from reaching consumers. Once it reach consumers, the recalls, the litigations, those things you don't need to happen. So speed here matter. That's what we demonstrated with our example. The second lesson is documentation is crucial here. Every decision must be traceable. Thirdly, the root cause analysis prevents recurrence. Always don't cure the symptoms. You need to go to the root cause and make sure it never happen again. That's the best practice. The other lesson we learned there is the pre-planned corrective actions enable faster response. So have as much as possible of pre-plan, as practicable as possible. And then we learned that the verification ensures corrective actions are effective. So we need to have verification, right? Ah. Now, let's look at the 12th step. Step 11. This is before the last step. Step 11, which is correspondent to principle 6, right? And is to establish the verification procedure. Okay? So what this step requires? It requires to establish procedures to confirm that the HACCP system is working effectively. All right? So why does this step matter here? Step 11, the monitoring tells you if CCP are under control right now, and verifications tell you if your entire CCP system is working as designed over time. All right? Now, let's look at the verification versus monitoring. We have an entire course here that you can find in our YouTube channel that will give you in-depth of verification versus validation versus monitoring. Now, if we look at this critical distinction here between verifications and monitoring, first, the monitoring happens at real time, all right? And is performed by line operators usually. The frequency sometimes is continuous, automated, or very frequent. All right. And the purpose of monitoring is to detect loss of control at CCP. Wait, and then the example will be measuring pasteurization temperature every seconds, and the actions, the questions it answers here, the monitoring answer, it answers to the question, is this CCP under control right now? That's the question you answer uh, with your monitoring. All right. But then if we look at the verification you have, if we look at verification, all right, verification is a system validation and is performed usually by QA personnel, the management, third party, and the frequency of verification is periodic. It's done either daily, weekly, or monthly. The purpose for verifications is to confirm the entire system worked as designed. All right. And the example will be reviewing temperature charts, calibration equipment, testing finished products, and testing. This verification will answer to the question, is our HACCP system effective? Now, let's look at the types, okay? The four types of verification activities. The first type of verification activity, you have validation. Validation always happen, as we said earlier, validation happen before the implementation, before you conduct any change, you must validate. So that's the first type of validation. First type of verification is validation. And you obtain scientific evidence that the CCP, the hazard plan, will control the hazard. All right. And I will show you later on how to conduct the validation. Example here is challenge studies proving that cooking time temperature kills the pathogens. That's a validation. And also scientific literature supporting critical limits and inoculation studies for acidified food and heat penetration studies for canned food. And then uh, when are you requiring that? As we said before, implementing new hazard plan, and when changing critical limits, and when changing processes or equipment, and when new hazards are identified. In all these scenarios, you must require a validation before the implementation. Then you have the second type of verification is calibration, which is ongoing. You do it ongoing to ensure the monitoring equipment provides accurate measurement. Example of calibration will include the thermometer calibration that is done daily using ice water and boiling water, and also the pH meter calibration that is done before each use with buffer solution, and metal detector sensitivity verifications that's done hourly with test pieces, and scale calibrations that is done weekly with certified weight, and water activity meter calibration that is done monthly with salt standards. The frequency here it must be based on equipment manufacturer recommendation and regulatory requirements. So this is the second type of verification is calibration. The third type is record reviewing, which is also ongoing. So you review the record reviewing. You review monitoring records and corrective actions reports to identify the trends. Again, you remember the best examples. So that's the purpose of reviews. Example is to review daily review of CCP monitoring log by QA to see the deviations and to determine the falsifications or any type of red flags, and also apply the corrective measures such as retraining or trends identification, etc. And then you have also weekly review of corrective actions reports by the management to apply the continuous improvement. And thirdly, you have monthly trend analysis for monitoring data, which is one of my favorite. And then you have quarterly review of all the HACCP records. And what to look for here? When reviewing, you are looking for deviation approaching critical limits, early warnings, and you are looking for recurring deviations for system design problems to fix it, and you are looking for incomplete records for training issues to conduct effective training, and you are looking for patterns indicating equipment degradations to implement also preventive actions. This is the third type of verification. And then the fourth type, the final type of verification is finished product testing, which is done periodically. And the testing finished products is done to verify hazard are controlled. The, h- the example here will be microbiological testing for Salmonella, Listeria, and E. coli control, and also chemical testing for allergen and pesticide heavy metals, and also the physical testing for metal detection verification, and pH testing of acidified products, and water activity testing of dried products. Important here to note that the product testing is a verification, it's not a CCP. And I've seen a lot of people will use, oh, I have CCP, I test the finished product. No, it's not a CCP, it's a verification, all right? So testing results come too late, as you know, to they are too late to prevent the unsafe product from being produced. So they cannot be CCP, right? Now let's demonstrate with real world example the verification schedule for pasteurized milk. So we have daily verification for pasteurized milk. What do? We calibrate thermometer. We dip it in ice water to indicate 0 degree Celsius and in boiling water for 100 degree Celsius. And we review previous day's temperature charts for deviations, and also we verify flow diversion valve operating correctly, and we review CCP monitoring logs for completeness. This is our daily verification for pasteurized milk. And for our weekly verification, we conduct microbiological testing of finished products with the standard plate count and coliforms, and we review all the corrective actions reports, and we verify cleaning and sanitation effectiveness with environmental swab techniques, and we conduct trend analysis for pasteurization temperatures. This is our weekly verification for the pasteurization milk, and you can take note and implement such robust verification. And then we have monthly verification for our pasteurized milk. We conduct independent temperature verification using data logger, and we calibrate flow meters. Uh, we calibrate flow meters to check the effect of resident time calculation, and it must achieve the minimum resident time. And then we review and update the HACCP plan if needed, and we conduct management review of HACCP system performance. Those are our monthly verifications for pasteurized milk production. And then we do have quality verification quarterly verification. We have third-party audit of HACCP system, and we have comprehensive microbiological testing, including pathogens, and we have equipment maintenance and validation, and we have HACCP team meeting to review system effectiveness. This is our quarterly verification. And then we have our annual verifications for pasteurized milk. We have complete HACCP plan as reassessment, and we have validation of critical limits to review new scientific literature, and we have comprehensive system audit, and we have update the hazard analysis. These are our verification, annual verification, and you can replicate the same, all right? The same way. This is for pasteurized milk, but you can do it for any product to have daily verification, weekly verification, monthly verification, quarterly verification, and annual verification. All right. Now, if we look at the world-class practices, the best practices in the world, first, you can assign verification responsibility to personnel independent of monitoring. And we stress this a lot in our courses, that the verification should not be done by the same person. It must be done by independent person to have a fresh eye. The same person always develop bias and also blind spot, right? Secondly, in the best practices, you document all the verification activities with dates and signatures, and also you use verification data to continuously improve the system, and you conduct unannounced verification checks, and you include verification in management review meetings. Those are the best practices in the world that you can replicate, and you will improve your system. Now, the common mistakes to avoid also is confusing monitoring with verification and relying on solely on finished product testing and inadequate calibration frequency, and not acting on verification findings, and also verification performed by the same person who does monitoring. As we said, that's a no-no, right? Now, the tools you can use tomorrow, take with you and do it at your work and improve the system, is to create a template for verification schedule and verification activity checklist, right? This can improve dramatically. Now, let's look at verification examples, all right? Before we move to step 12. We have real world verification examples here, and we have comprehensive verification example. The first example will be equipment calibration verification. And here we have the thermometer calibration daily. The equipment is digital prop thermometer used for cooking CCP. The calibration methods here: first, ice water test at 0 degrees Celsius reference. So what do? We fill the container with crushed ice and water. Oh, wait. And then we insert the thermometer prop into the ice slush. Then we wait 30 seconds for stabilization. And then the reading should be 0 degrees Celsius plus or minus 1 degree. All right. And if outside the range, we adjust or replace the thermometer. And you can do this calibration too. Then we have also in calibration method, we have boiling water test at 100 degrees Celsius reference, and we adjust for the altitude. All right. So we bring the water to rolling boil, and then we insert the thermometer prop, and we ensure that it doesn't touch the container, and we wait for 30 seconds for stabilization again. And then the reading should be 100 degrees Celsius plus or minus 1 degree at the sea level. And we adjust for the altitude minus 1 degree Celsius per 300-meter elevation from the sea level. All right. Now, the documentation required here, we have calibration log with date, time, ice water reading, boiling water reading, corrective action if we have any, and technician signature. And then if thermometer fails, the calibration we remove from service tag, and we tag it with out of service or out of calibration, and we replace it immediately. The frequency of doing so, we do it daily before the use. All right. That's example one of daily thermometer calibration. In example two here, we have record review verification. I'm giving you diverse examples, right? We have record review verifications, and here we have CCP monitoring log review is done daily. And what to review here? All the CCP monitoring logs from the previous day. We review the checks for the completeness. All the required entries must be filled, and we verify all the readings within the critical limits. And we review to confirm all the deviations have corrective actions reports, and we check for trends approaching the critical limits so that we can take actions. Our review checklist consists of all the time entries must be present and sequential, and all the temperature parameters must reading and recorded, and all the readings within the critical limits, and operator initials present for all the entries, and any deviations must be properly documented, and the corrective actions must be completed and signed, and also no unexplained gaps in the records. Now, I want you to pay attention here. You need a review checklist. I've seen in many organizations where people just go randomly to check, go for inspection, check and say everything is fine. Sometimes you forget, or sometimes you don't pay attention for the details, but you must have a checklist to check against the reviews. All right? And this will make you pay attention to the details. All right? And your technicians can take this checklist and also go and do the review. Now, you must watch for the following red flags: the suspicious perfect data, where all readings are identical. Watch out for that. And missing time periods, and readings exactly at critical limits. This may indicate fabrication. Pay attention to that. And illegible entries or alterations, and also patterns of readings just above or just below the critical limits. Watch out for that. And the same handwritings for the entire shift, that suggests the batch recording. They just recorded at once. All right. The actions on findings also, you need to have the classification. First, for the minor issues, you need immediate retraining. For the pattern of issues, you need to investigate the root cause. For the suspected falsifications, you need to involve management investigation and potential disciplinary actions. And for the gaps in monitoring, you need to evaluate product safety and implement corrective actions. And for the documentation required here, you need record review checklists must be completed daily, and summary reports of the findings and the follow-up action must be documented. All right, this is how you conduct the review, uh, record review verification. You can take all these notes and design yours tailored to your organization, and this will give you a roadmap. Okay. Now we move to example 3, the finished product testing verification. This is also a general best examples. Microbiological testing is done weekly, and the product here is ready to eat sliced deli meat. And the hazard here is Listeria monocytogenes for post-processing contamination. The test protocol here, we sample for the sample collection. We take 5 packages randomly selected from production, and then the sample size is 25 gram composite sample. You know, composite sample also require technique, right? Composite sample from each packet, so totaling at 125 grams. And then the test method is based on ISO 11290 volume 1 for detection, or ISO 11290 volume 2 for enumeration. And for the laboratory, we need accredited third-party lab. And for the turnaround time, we expect between 48 to 72 hours. And for acceptance criteria, for Listeria monocytogenes must not be detected in the total samples of 125 grams. And if detected, immediately we hold all the products from the same production day. For interpretations, pass means we will release. If we not detected, we will release the product and continue the routine testing. But if it fails, if we detect the Listeria monocytogenes, we initiate the recall of procedures, we investigate the results, we intensify the environmental monitoring, and we review sanitation procedures. For environmental monitoring also, which is concurrent, and we have the entire course on this, you can find it on our YouTube. The test production environmental for Listeria species here. First, the zone tested. In zone 1 is food contact surfaces. This is conducted daily. Is zone 1, and for zone 2 is near food contacts. We conduct the tests weekly. And for zone 3, which is a remote from the food contacts, we do the testing monthly. And for positive environmental reserve, it triggers the investigation even if the product is negative, right? Pay attention here. When you conduct your environmental swaps, any zone must have a systematic actions requirement in case of positive tests, even in zone 3. All right. And I will show you example now. All right. Now, for example, number 4, we have independent processing verification. Example. Okay, let me go back here, just in case you need this. The example of finished product testing verification. You can also replicate and take the best practices and replicate them in your organization, and all the best. Now, example number 4 is independent process verification. Here we have pasteurization validation is done annually. And the purpose here is to verify that the pasteurizer achieves critical limits throughout holding tube. All right. The methods here is heat distribution study using the data loggers. The procedure here is to place 10 wireless temperature data loggers throughout the holding tube, and then to run the pasteurizer at the normal operating conditions, and then to record the temperature at each logger position every second for 2 hours, and then to analyze the data for all its parts. All right. The acceptance criteria: all positions must maintain below above 72 degrees Celsius for the entire holding time, and the temperature variation across the holding tube must not be more than 2 degrees Celsius, and no cold spot below the critical limit, not acceptable at all. All right. And the results documentation here: the temperature profile graphs for all the luggers positions, and also the statistical analysis, including mean, minimum, and standard deviation, and identification of any cold storage, cold spot, and validation reports signed by qualified process authority. All right. Then the actions on finding also. In case of pass, that means the pasteurizer is validated for another year. But in case of fail, if we need to identify the root cause, why do we have cold spots, flow patterns, heat distribution, whatever the root cause is, we will modify the equipment and revalidate again. All right. This for pasteurizer. If you want to conduct your independent process verification for pasteurizer validation, annually you can follow this as the best practices, one of the best practices in the world, right? Now, example 5 is third-party audit verification. For third-party audit verification, we have HACCP audits. The best practice is to do it quarterly, okay? For HACCP system audit. The auditor here is an independent third-party certified certification body. The audit scope include first to review the HACCP plan for the completeness and accuracy, and to verify implementation of all the HACCP procedures, and to review monitoring records for the past 3 months, and to observe monitoring activities in real time, and also to review personal performance monitoring, personnel monitoring, um, uh, performance monitoring, and to verify calibration of all the monitoring equipment, and to review corrective actions reports, and to verify verification activities are performed, and also to check the prerequisite programs supports the HACCP. All right. Now, the audit findings categories here. You have the audit findings. You have critical, that means immediate food safety risk. That's the categorization of critical, and it requires immediate corrective actions. And for the major findings, that means it's a system breakdown and it requires corrective action within 30 days. And for minor findings, that means an isolated deviation and requires corrective actions within 90 days. And for observations, that means this is an opportunity for improvement and doesn't require any corrective action. For the follow up, corrective action plan for all the findings must be presented, and the root cause analysis for critical and major findings must be presented. Verification of corrective actions effectiveness must be presented, and re-audit if the critical findings are identified. All right. For the real world best practices for validation practices, first you use multiple verification methods and you don't rely on just one, and you assign verification to operational independent of production, and you schedule both announced and unannounced verification activities, and you the trend verifications data over time to identify system weaknesses. You use the trend, and you use the verification findings to continuously improve the HACCP system, and you document all the verification activities thoroughly, and you include the verifications in management review meetings. All right. Finally, we are here in step 12. All right. Let's do step 12. And then we can, the next video, we will do the GMP or the prerequisite programs. But now let's complete the step number 12 for the complete implementation of HACCP. Now, In step 12 is to establish the documentation and record keeping. All right. Seems easy one, but this is the life. This is the mirror. This is the proof that you have HACCP. If you don't do it, that means you don't have HACCP, my friend. So what this step requires is to establish the procedure for documentation or for documenting the HACCP system and maintaining the records that demonstrates the system is working. So why this step matter? Like I said, documentation proves your HACCP system exists and works. All right. Record provides evidence of control, and without documentation, you cannot demonstrate compliance or defend yourself against liability claims in case. All right. Now, there are two categories of HACCP documentations here. You need to pay attention to that. The first category, my friend, is the HACCP plan documentation. All right. In this category here, the HACCP plan documents, these describe your HACCP system and what you will do, not what you are doing, what you will do. And here, the required document first, you have hazard analysis worksheet. You need to have it. This means the hazard analysis worksheet should include all identified hazards, an evaluation of each hazard, the likelihood and the severity, and also the control measures for each significant hazard and justifications for the decisions. So this needs to be included in your analysis worksheet, hazard analysis worksheet. Secondly, you need to have the hazard plan summary table. And in your summary table, you should have process, must include process steps and identify hazards and critical control points, CCP, and critical limits and monitoring procedures, the what, the how, the frequency, the who, all right, and corrective actions and verification procedures, and also the records, all right. And then the third document you need is the set of documents are the supportive documents, and those supportive documents must include product description, intended use statement, process flow diagram that must be verified on site, of course, not in the office, and CCP decision tree application, and scientific justification for critical limits, and validation studies and standard operating procedures, SOPs, for each CCP. All right? This is your first category, those set of documents. All right? Now, your second category is HACCP records. And these documents will like they demonstrate what you actually did. The first set is what you will do, right? All this set of documents, what you will do. But the second category is HACCP records of what you will do. And the required records here, first, you need CCP monitoring records. Those include date and time, actual value measures, operator signatures and initials, and deviation noted. Then secondly, you need correct action records. This must include the description of the deviation and the product affected, the batch and quantity, and the product disposition decision included either to release, reprocess, or destroy, and then the root cause analysis, and also the preventive measure implemented, and verification of effectiveness and signature and date. All right. Then the third, you have verification records. That's the third set of documents you need in the second category, including the equipment calibration logs, record review checklists, finished product test results, audit reports, validation study results, and signature and the date. Then you have the third set is the training records must include employee's name, training topic, date of training, and the trainer name and assessment results. All right. Now, let's look at the record retention requirements. And of course, the minimum retention periods varied by the regulations, but generally the frozen or shelf stable products, the record retention period is 2 years beyond shelf life, and the HACCP plant retention is 2 years beyond the last use. And for refrigerated products, the record retention is 6 months to 1 year beyond the shelf life, and the hazard plan is 1 year beyond the last use. And for the general best practices, the CCP monitoring records are kept for 2 years at the minimum, and also the corrective actions records are kept for 2 years at the minimum, and the verification records also at 2 years at the minimum, and the hazard plans documents also are kept at 2 years at the minimum after the revision. All right, and the training records duration of employees plus the 2 years of at the minimum. Now, the record storage requirements here, in case of physical records, must be protected from the damage from water, from fire, from pest, and must be organized for ease retrieval, and must be access controlled, and must prevent tempering, and backup copies and stored off-site. For the electronic records, must secure system with access control and audit trails, who access it, when, what change, and regular backup and disaster recovery plan and compliance with 21 CFR Part 11 if that's applicable to you. Now, to demonstrate with real world example, the complete HACCP documentation for cooked chicken, you have first, we have HACCP plan, document structure. This is a complete documentation for cooked chicken, okay? So the HACCP plan documentation structure, you start with the cover page. In cover page, must have company name and address, the product name, cooked chicken breast, and HACCP plan revision and date also must be included in the cover page, and approved signature with HACCP team and plan manager and QA manager on the cover page. Then secondly, for the product description, include the raw material is fresh chicken breast. The processing uh, must be marinated, cooked to 74 degrees Celsius of internal temperature. The packaging is vacuum sealed plastic pods. The storage refrigerated at 0 to 4 degrees Celsius. The shelf life is 21 days, and the distribution is refrigerated transport, and the intended use is ready to eat, and no further steps required. And the target consumer is general public, including vulnerable populations. Then thirdly, you have the process flow diagram that includes, and definitely is a visual process flow diagram, but descriptive text here for illustration, from receiving to cold storage to monitoring to cooking, which is the first CCP, to cooling to slicing to packaging to metal detection, which is the second CCP, to cold storage and to distribution. This is the process flow diagram. Then we move to hazard analysis table. In hazard analysis table, we must have a detailed table showing all the steps, all the hazards, and all the significancy and the control measures. And then we move to the hazard plan summary table. This table must be a complete table with all the 7 principles for each CCP. And for the supporting documents, we include the CCP1 cooking SOP, the CCP2 metal detection SOP, the thermometer calibration procedure, and the metal detector validation study, and also the corrective action procedure, and the verification schedule. For the daily record generated, we have in monitoring, we have thermometer calibration log at 6 a.m., the metal detector test log at 6:30 a.m., the CCP1 cooking monitoring log start at 7 a.m., and the CCP2 metal detection monitoring log start at 8 a.m. And throughout the day, the records generated, we have continuous entries on monitoring log and corrective actions report if deviations happen. At the end of the day, we generate the record review checklist is completed by the QA and any verification activities performed. All right. Now, for the documentation best practices, you should make it easy, make it simple, one page monitoring, okay? one-page monitoring forms when possible, and pre-printed forms with checkbox and clear instructions on each form and minimal writing requirements. Okay. Secondly, make it accurate. Make your document accurate. Must record in real time, not at the end of the shift, and use ink, not the pencil, and also no white out, and include the date and time. Thirdly, make it accessible. Store records near the monitoring locations and organize chronologically and index for ease retrieval and digital copies for the backup. And fourth, make it defensible, must be complete all the fields, sign dates and entries, and document all the deviations and maintain chain of custody. The common mistakes to avoid here: first, the incomplete records, missing signatures and dates, avoid that, and also the batch recording all at once, avoid that. Altering records without proper documentation, using vague language like cook until proper, and not documenting the corrective actions, and poor records organization, and inadequate backup, and also the records not reviewed regularly. Avoid these mistakes, all right? Tools you can use tomorrow: complete the HACCP documentation backup, including the HACCP plan template, monitoring log template, corrective actions template for form, and verification checklist, and the record schedule. All right. Thank you. And next, I will give you prerequisite programs. All right. I'm giving you prerequisite program